Good day, dear participants. It's a great pleasure for me to see so many new faces at our conference. I'm delighted to introduce our first speaker. He is Professor Andrei Teleman from Marseille, France.
Okay, so you see the title of my talk contains a classical problem integrated in the title, the Riemann Hilbert problem, and a set of modern notions, bundles framed along real hypersurface. It's a moduli theory in complex geometry. So I will try to explain at the beginning. So you'll see here the structure of my talk. I will start with classical old problem, so 1912. The Riemann Hilbert problem. Then I will I will go on with the second section, in which I explain the tools, the theorems I used to handle this classical problem, and in a certain sense to solve it, at least to give geometric interpretation of the space of solutions. And finally, I explain you an application in modern gauge theory. So in modern geometry. Okay, so let's start. Just a moment, please. So the Riemann Hilbert problem we are interested in is stated in a famous book, Grundzüge einer allgemeinen Theorie der linearen Integralgleichungen. I don't even dare to translate it into English because it became so famous, so classical, and of David Hilbert, and more specific, deals with a problem formulated and handled by Hilbert in this chapter 10, the problem of Riemann in the theory of functions of one complex variable. So using modern terminology, this problem can be stated as follows, in a very simple, clear way. So a Riemann Hilbert problem, the input data of a Riemann Hilbert problem is a very simple object, is a pair S gamma consisting of a simple, compact, connected curve in C. For instance, the circle S1, you can think already that S is a circle S1. And a map defined on S, only on S, with values in a, let's say, in a general linear group, GLRC, of class C kappa. So as you see here, I work with non-integer, not necessarily integer differentiability class. When K is non-integer, I mean Hölder, differentiability in the Hölder sense. I will not insist on this analytical technicalities, although probably analysts here present in the conference will be interested to see more about this. Okay, so I will denote by U plus and U minus the two disks, the two connected components obtained if one cuts the Riemann sphere P1 along S. So if one cuts the Riemann sphere along S, then we'll get two disks, two open disks, U plus and U minus. By U plus, I mean the disk which contains the infinity, the point and infinity. Okay, so the Riemann Hilbert problem associated to our pair S gamma as the following, very natural. Find the space of all pairs F minus F plus consisting of continuous maps. So F plus is on the closure U plus bar of U plus and F minus on the closure U minus bar of U minus, which are holomorphic on the interiors and whose restrictions to S are related by gamma. So satisfy this relation. Let's say are gamma compatible. If F minus is nowhere vanishing, of course, you just can't say that we fix the ratio, the quotient of F plus by F minus along gamma. Very natural problem. More generally, you can allow F minus. We can still formulate a new problem, more general one, in which F minus is still required to be holomorphic, but we allow F plus to be meromorphic with poles in U plus, for instance, at infinity. And now I come to, I will quote a Slovenian mathematician, but I have a surprise for you. When I read his article, I noticed that he was professor in Czernowitz. Okay, so it's an article written in 1908, before Hilbert. It became famous for his contribution to the subject. At that time, Czernowitz was part of Austrian Empire, but as his spirit is still there, I believe, where he was a professor. So yes, this is the refinement of the Riemann Hilbert problem as stated and solved by Plemage in Czernowitz in 1908. What the difference here? It's absolutely the same. We ask of the space of pairs F minus F plus, where again F minus is required to be holomorphic, on the disk, on the disk, which is included in C, and F plus meromorphic on U plus. But what we allow F plus to be meromorphic. However, we ask to have a single pole with prescribed singularity type at infinity. So we allow pole only at infinity. This is the Plemage version of the Riemann Hilbert problem. Prescribed singularity type means in fact to prescribe the Laurent coefficients of non-positive index at infinity. Okay, so now let me generalize Plemage version in a natural way. Namely, I will fix a complex Lie group G, not necessarily GL. This is a natural generalization nowadays. So I'll fix a representation. So this means a morphism of Lie groups from G to GLV, where V, of course, is a finite dimensional complex vector space. Again, a map, this time with values on S, on the curve, with values in G of class C kappa, the same formalism. I will fix M in Z, and I will fix a polynomial with coefficients in V, in one variable. And I will denote by its degree with the convention that when the polynomial is 0, by convention, its degree, it's by definition -1. Okay, and now for complex geometry, it's very easy what I'm writing now. For the others, maybe it's mysterious. So I will regard this point at infinity as an effective divisor on P1. And with this geometric point of view, gamma can be interpreted as an element of this space of sections, in the sense of complex geometry. What sections? It's a torsion sheaf on P1, a skyscraper sheaf concentrated at infinity. But in the formals of complex geometry, of modern complex geometry, I can consider the D+1 multiple of this point. So this is not a multiplication in the sense of numbers, but is this the divisor, the point at infinity regarded as a divisor taken with multiplicity D+1. So we have a complex space, a non-reduced complex space, on D infinity. So this is a sheaf on this non-reduced complex space. And the whole sheaf, which is written here, can be regarded as a torsion sheaf on P1. Okay, gamma can be interpreted as an element of this space of sections, of a coherent sheaf on P1, torsion coherent sheaf on P1. Okay, and then we ask, find the space of pairs in the same spirit as the original Riemann Hilbert problem, y minus y plus. Again, continuous maps, continuous maps on the closed disks, on the closed disk. Of course, on the plus side, we don't have continuity at infinity because there we have a pole. Yeah, but we ask y minus again to be holomorphic on on u minus, y plus to be holomorphic on u plus minus the point at infinity. Again, we require the gamma compatibility on the curve, yeah, and at infinity, I require a condition which controls the behavior at infinity of y plus. So it's meromorphic. It's too vague. It does not allow me to describe in a precise way the space of solutions. So I refine the Plumage version, which is it's also a refinement of original Riemann Hilbert problem, in which I control with precision the behavior, the growth on the decay of y plus at infinity. And this is the natural condition. Why I say this is a natural condition? Because this condition can be interpreted again with in the complex geometric formalism as follows. This limit condition can be in complex geometry interpreted like that. Y plus extends as a section of the sheaf. I take the trivial sheaf associated, the free sheaf associated with V, with fiber V, and I twist it with m times the divisor. As I said, the point infinity considered as a divisor on P1. I multiply it with m, and I obtain a non-reduced divisor on P1, and this is the invertible sheaf associated to this divisor, to this effective divisor. Okay, and the free sheaf of fiber F is twisted with this locally of this invertible sheaf. Okay, so Y plus extends as a section in this locally free sheaf, yeah, whose image in the complex space, as I said, non-reduced complex space, d plus 1 infinity with multiplicity d plus 1, via the obvious isomorphism is precisely the element in this H0 space associated to gamma in a natural way. So of course, here it's mysterious what I say here, probably for people who are not accustomed with complex geometry formalism. It's not a problem. Here, what is important is that I wrote an analytical condition which controls the behavior of Y plus at infinity, the growth or the decay, and that this condition has a clear geometric interpretation in terms of complex geometry. So coherent sheaves, I'm using here coherent sheaves and complex spaces. Okay, now Hilbert's original problem is obtained taking rho to be the canonical representation of GL RC on Cn, taking m is 0 and gamma also the zero polynomial. And then now obtains with these choices, one gets exactly the original Riemann Hilbert problem. Plumage problem is obtained with the same rho by taking here m equal d. In this case of the twisting sheaf here, the twisting index m coincides with the degree of the polynomial, then one gets exactly Plumage problem. And also I mentioned here matrix factorization problem. If you Google Riemann Hilbert problem, then you will not be, this I mean, in my opinion, is the omission of the mathematical community. You are not sent to the papers of Hilbert and Plumage as it should be, but to a more modern version, what are called matrix factorization problem. I don't get into details here, but if you go to Wikipedia and Google Riemann Hilbert problem, we'll find a very interesting page which deals with matrix factorizations problem, and they can also obtain as a special case of the general formalism. Okay, now what is the new point of view about these classes of problems? Yeah, so the last one being what I call the Riemann Hilbert problem on P1. I come with a complex geometric point of view, which, as far as I know, is new. So what I consider is the sheaf of local solutions of the Riemann Hilbert problem in the simplest case, in the simplex case, in the Plemmel situation where M is gamma is 0. What does it mean exactly? What is this sheaf? This sheaf can be defined in the following way. So for me, the sheaf is a pre-sheaf which satisfies the usual conditions of completeness and separateness. So this, regarded as a pre-sheaf, this sheaf is defined explicitly in the following way. So exactly what I say here, the space of local solutions. What this means for an open set in P1, which this open set might intersect S. So for a open set W in P1, I take the vector space of all pairs F minus of plus of solutions of the Riemann Hilbert problem, but formulated on W, which means that F minus is no intersection W with U bar minus, continuous on this intersection, F plus the same with U bar plus, again, continuous on this intersection. I require holomorphy on the intersections of W with INA, with the interiors, and on the intersection with S, I require, as usual, gamma compatibility. So this can be done for every open set in P1 in the Riemann sphere. And this is a theorem which I obtained. This, in fact, is a corollary of a gluing theorem I will mention later, which tells that this sheaf, which is obviously a sheaf of P1 modules, is locally free, of having the same rank as the dimension of E, and coincides with the apparently smaller sheaf defined in the same way. But you see here, I impose class CK up to the boundary. Here I impose continuity. Here I impose differentiability of order CK. Of course, you'll be astonished. How is this possible that continuity implies K differentiability? The explanation is that we don't have only continuity, but on the interiors, we have holomorphy. And this explains, this means that imposing holomorphy on the interiors and the gamma compatibility together give us K differentiability of F plus and F minus up to the boundary. We have now, if I compare, so I mentioned already this torsion sheaf on P1. Again, I take the infinity regarded as a point as a divisor. I multiply it with D plus 1. I obtain a non-reduced divisor. So D plus 1 is a multiplicity of the point infinity in this divisor. I twist with invertible sheaf the infinity. This is a locally free sheaf on U plus. And one can see that we can identify, first of all, in a natural way, the sheaves, and then, of course, the space of sections. So gamma, in fact, gives me an element in this sheaf, which I constructed, which I have already, that my theorem produced a locally free sheaf, which I denoted by V gamma, V calligraphy gamma, and gamma gives me an element in this space of sections. Again, here what we have is a torsion-free, a skyscraper sheaf concentrated at infinity. Okay, now this is absolutely elementary in complex geometry. Here we have a short exact strength, a coherent sheaves on P1, which are associated to the, here one can consider the epimorphism, defined in this way, which this epimorphism is very geometric. I take a section in this sheaf and I look at its restriction to infinity, but not only to the point infinity, but to its D plus 1 multiple. So I look at this, here, the section, I take a section here, and I assign to a section its restriction to the divisor infinity multiplied with D plus 1, with multiplicity D plus 1. So if you say what I take the D plus 1 ordered jet of my section. Okay, so this is an exact, a short exact sequence of sheaves, and then you know the story. Then I have a long exact cohomology exact sequence. Yeah, and this cohomology exact sequence contains the famous delta, so the connecting operator, which goes from H1 of this, or H0 of this, yeah, to H1 of this. And this is important because my new gamma is, so the object associated to gamma is an element here. And then my corollary states the following. In a certain sense, this corollary solves the general Riemann Hilbert problem, which, as I said, generalizes Plemmage version, which generalizes Hilbert version. So it says the following. The space of solution is non-empty if and only if the image of the object here, so new gamma gamma I constructed is associated with gamma. Yeah, of course I have to twist it with this element, with this section, in order to land here. Okay, so the space of solution is non-empty if and only if the image of this object, which is essentially gamma, yeah, it's essentially gamma, the polynomial, the given polynomial, vanishes. Yeah, this is a clear existence theorem for solutions. So this solves the existence problem. Okay. If this is the case, if this existence condition is satisfied, this space has a natural structure of an affine space, and I can precise what is the modal space of this affine space. Yeah, this is the space of section. This is a very easy sheaf. Yeah, this is a sheaf I've constructed. Yeah, the gamma twisted with a multiple of the point of infinity, again interpreted as a divisor. Okay, and can be identified with the pre-image of our, again, element associated to gamma via this morphism of space of H0s, yeah, of spaces of sections. I should say that all these objects are easy complex geometric objects. I will explain this later. So this means that as soon as this sheaf is known, yeah, these sheaves, the existence of whom that I proved, the theorem states, my theorem states that this sheaf is locally free, coherent locally free. As soon as this sheaf is known in a sense I will precise immediately, then everything can be solved. So one can answer when the space of solution is empty and to describe it. Okay, and also one has a regularity theorem, yeah, which says that in this very general framework, any solution of a Riemann Hilbert problem of class C kappa, yeah, is in fact of class C kappa up to the boundary. So in the problem, we impose only continuity. Gamma is of class C kappa, yeah, but a priori for the pair y plus y minus, we impose continuity and holomorphy on the interiors. And what I say, as soon as these conditions are satisfied, that in fact we have class C kappa up to the boundary. Important. By Grothendieck's theorem, we know all coherent sheaves, locally free coherent sheaves of bundles, holomorphic bundles, if you wish. It is the same on P1. Yeah, it's a Grothendieck, a famous theorem of Grothendieck, which says that any locally free sheaf, if you prefer any holomorphic bundle on P1, vector bundle on P1, splits as a direct sum of invertible sheaves, so the line bundles, yeah, if you prefer the terminology of bundles. So invertible sheaves are locally free of rank 1, yeah, so they correspond to line bundles. So this means that the sheaf I obtained, Grothendieck says that it's in fact a direct sum of sheaves which we know very well. Yeah, this canon on P1, which are defined in any elementary book on on algebraic geometry. Yeah, so these are the fundamental twisted invertible sheaves on P1. So this is the fundamental, the structure sheaf twisted with an integer. Okay, and one can the integrals ng. Of course, this is a problem. It's what can be said? One can be said about these integrals. One can say is that the sum is precisely the degree of V gamma, and this can be computed. It's a topological invariant, which of course should be prescribed by gamma. And indeed, yeah, for instance, if you take the canonical representations of GLRC, as in Hilbert's and Plemage version, then the degree of this coherent sheaf, of this locally free coherent sheaf, is precisely minus the degree of determinant of gamma in the topological sense. So here the topologists would be very happy. So the determinant of gamma is a map with values in C star, yeah, whose fundamental group is Z, and yeah, S is essentially topologically a circle, so you can speak about the degree. Okay, so what is the conclusion? That once when we are in the possession of the complex geometric objects associated with gamma, yeah, associated to our input data, the corresponding Riemann Hilbert problem can be approached and solved using elementary complex geometric methods. This is the conclusion. Yeah, so, but the difficulty, you see here, it's maybe instead of hurrying up to go on and to come to difficult theorems, maybe it's better to comment a bit about this conclusion together, because this results, I think, illustrate the fundamental difference between fundamental mathematics and applied mathematics. From a pure mathematical point of view, I can say, okay, the problem is solved, because as soon as we have our input data, the representation, the map gamma on the curve, and the polynomial small gamma, then I construct in a very explicit way a coherent sheaf. I prove that it's locally free of known rank. I apply the Grothendieck theorem, and then I come to complex geometric objects which are easy, and then the problem can be solved. But an applied mathematicians will say, wait a minute, but given gamma, how can you explicitly determine your coherent sheaf? And how can you prescribe the integrals NE which intervene in the Grothendieck decomposition? Yeah, so this is in fact from a point of view of applied mathematics, I cannot say that the problem is solved. From point of view of pure theoretical geometry, it is. So anyway, however, the method is effective. For instance, if one can say one can want examples, yeah, explicit examples. Give me list explicit examples of such data for which the space of solution is empty. Then, of course, I can do it, because I can start with the complex geometric objects, yeah, and then I take examples of gamma which correspond to complex geometric objects. So in the opposite sense, the procedure is much easier. And also, yeah, we can get effective results. So at least from small r, yeah, for small r, so r is if I take it's the number which intervenes in GRC, the dimension of V essentially. And standard representations, one can compute all the possible dimension of the space of solutions for a given Grothendieck decomposition. So as soon as I know the Grothendieck decomposition at the gamma, I can list what are all possible dimensions of the space of solutions which can occur. So, as I said, a difficulty remains, given gamma, determine explicitly a Grothendieck direct sum decomposition of the gamma and the position of this element. Yeah, this again is a section in a torsion sheaf on P1 with respect to the summons. So this is from the point of view of applied, of effective mathematics. This is the problem which remains to be solved. Okay, so generalization to Riemann surfaces. This is also a thing which, in my opinion, was very natural to do, and I didn't see in the literature. One can generalize everything to a closed Riemann surface, not necessarily to P1, and S in X, an arbitrary, this is new. Generalization to Riemann surfaces I saw in the literature. But then by tradition, always S is assumed to be a separating curve. Now, one can consider an arbitrarily oriented, not, of course, every curve, closed curve is orientable. No, but here I orient it, which means I orient every connected component. Yeah. So S X is a closed Riemann surface and S is an arbitrarily closed, oriented, real one-dimensional submanifold. But it's not necessarily connected and not necessarily separating. Yeah. And I regard the Riemann surface with boundary obtained by cutting X along S. Yeah. Its boundary decomposes as a direct sum of two copies of S, as you see here. So this, you see, this example shows everything. This is a Riemann surface of genus 1. S is a curve like that. I cut X along S, and you see S doesn't separate X. What I get is a Riemann surface with boundary. And in this case, I have only two components of the boundary, which are obviously, they are identified because both are identified with S. So I get an identifying diffeomorphism between these components of the boundary. But as again, S doesn't need to be connected. Yeah, if S is not connected, I can split the components of the boundary in two classes. Yeah, and then the corresponding disjoint unions can be identified. Okay, so again, the input data are a representation defined on G, on a finite dimensional vector space V. A map, I choose one of these connected components, for instance, S minus, doesn't matter which one, because they are identified via the blue map, yeah, B. Yeah. And I choose two divisors, so D and delta. So D is a divisor which I twist my sheaves, yeah, and delta is a divisor which I place the role at the point of infinity, or more precisely at its multiples, as its multiples. So delta is an effective divisor which is used to take the jets along delta. I will consider jets along delta of the sections I consider. Yeah. So delta generalizes this multiple d plus 1 times infinity. Okay, so instead of a polynomial, I take a section in this torsion sheaf. Yeah, torsion sheaf. So here is on X minus S, which is nowhere vanishing on delta. And then I formulate in this very general framework the Riemann Hilbert problem for the Riemann surfaces. Find the space of meromorphic maps on this Riemann surface with boundary, but on the interior part, I remove the boundary. Yeah, so on this part are meromorphic, are just meromorphic. But I ask them to extend continuously around the boundary, of course. Yeah, and then denoting by the same letter this continuous extension around the boundary, I require again a compatibility, gamma compatibility condition between the restrictions of Y to the two pieces of the boundary, which are identified via B. Very natural. After seeing that, I realized that it's more natural to work in this general framework with non-separating curves than as in the classical framework. Okay, and then I ask a condition, natural condition, which corresponds to this growth behavior of Y plus, if you remember. Namely, I ask that Y extends as a section of this sheaf, yeah, on X minus S. This means the free sheaf, in fact, associated to V, yeah, with fiber V, twisted with D. Yeah, so twisting with divisor, this is well-known procedure in complex geometry. Okay, and I impose the image of this extension in this torsion sheaf. So here, this torsion sheaf can be regarded as a quotient of this one. Yeah, so I just impose that the image of Y in this in H0 of this torsion sheaf via the obvious morphism is gamma. So it's a very natural generalization of the Plemage condition. So the homogeneous case corresponds to the case when the divisor delta is empty, is zero. Okay. Now the theorem stated above for the original Riemann Hilbert problem generalizes to this framework and gives an analogous theorem. Corollary. So the details are not so important here. Of course, they are interesting for complex geometers here, if we have complex geometers in audience. But for the others here, what is important is that, again, we obtain a solution, complex geometric interpretation of the space of solutions. But again, this complex geometric interpretation uses a sheaf. So as I said, the theorem stated above, the theorem says that a certain sheaf is locally free of rank the same as dimension of V. As soon as we have this coherent sheaf, this locally free sheaf, in a locally free sheaf, it means a vector bundle, holomorphic vector bundle, and then suddenly we are in the universe of complex and algebraic geometry, and you can use complex geometric methods. So again, the space of solutions in this framework is non-empty if and only if the image of this object associated to gamma via the obvious morphism vanishes. Yeah. Again, here we have the space of sections on in a torsion sheaf on X. This is important, yeah, on a closed Riemann surface X. Yeah, everything is on X here, which is a closed Riemann surface. And if this is the case, so if this existence condition is satisfied, then again, the space of solutions is an affine space. I can precise the Rödel space of this affine space, and I can say with precision what is it. The space of solution is a pre-image of the object, if this section in the torsion sheaf associated to gamma via the natural morphism we have between this space, H0 spaces. And also regularity. I mentioned this regularity. Maybe you wonder why always because Hilbert treats his regularity in his book. Yeah. So in particular, so I can obtain as a special case is Hilbert's regularity results. So any solutions of this general Riemann Hilbert problem with gamma of class C kappa is also class C kappa up to the boundary. Why? An interesting example, a special case, it's of an elliptic curve. An elliptic curve can be defined, yeah, an elliptic curve. So it means a Riemann surface of genus 1 can be obtained by factorizing C star. I factorize C star by a cyclic group generated by the multiplication with alpha, let's say, of contraction. I take an alpha, a complex number in C star with modulus strictly smaller than 1. So I factorize C star by a contraction, by linear contraction, complex linear contraction. And every Riemann surface of genus 1, every elliptic Riemann surface, elliptic curve, if you wish, can be obtained in this way. And I take S to be the image of S1 in X. What happens if I cut this Riemann surface along the circle S? I obtained an annulus. I obtained the annulus, namely here you see I take the set of complex numbers of modulus between R. Again, R is a modulus of alpha between R and 1, and the boundary is a union of two circles. And then you see we come to a version of the Riemann Hilbert problem completely new. Yeah. So this time, what we looking for, we no longer have an y plus and y minus. I want my problem looks for the space of solutions of the y's, of the maps y's, which are meromorphic on the interior annulus, extends continuously up to the boundary, yeah, and denoting by the same symbol the extension on the boundary, we impose this compatibility condition. So I impose a compatibility condition, a gamma compatibility condition of the restrictions of y to the two components of the boundary. So again, if let's say on S1 y is nowhere vanishing, this means that we impose the quotient of y, of the restriction of y, of two components of the boundary. Yeah, and here again on elliptic curves, we have a theorem by Atiyah, which again, as Grothendieck does on P1, so Atiyah's theorem classifies all the holomorphic bundles on an elliptic curve. So this means that the sheaf, this sheaf V gamma, V calligraphic gamma, which intervenes in my corollaries, in my results theorems, can be handled. So we know what are the possible sheaves of this type, what can be this sheaf V gamma. We have only a finite number of possibilities. Okay, then I explain what are the theorems which I use to obtain these results. I will tell you that my goal was not at all the Riemann Hilbert problem. I was working on problem of moduli spaces. I obtained a theorem, a gluing theorem for holomorphic bundles, and I suddenly realized that this gluing theorem can be used to approach the Riemann Hilbert problem. So what is here the problem? Now we go suddenly in the n-dimensional framework. So U here is a complex manifold, arbitrary dimension, and S in U a closed separating real hypersurface. So I work first with a separating case. What this means separating? This means that the complement splits as a disjoint union, Y minus of Y plus, okay, where the closures are manifolds with boundary and the boundaries are coincide with S. Yeah, this is very easy, separating hypersurface. And now on any manifold of boundary obtained in this way, U plus minus, I consider a say infinity complex vector bundle denoted A plus minus, and I also consider the restriction to S, denoted with the index here with a subscript S. Now, I consider a bundle isomorphism between the two restrictions. Yeah, bundle isomorphism of plus C kappa. Yeah, C kappa, the same, the Hilbert differentiability. As soon as I have this, I can glue E plus and I minus together via gamma in an obvious way. But one obtains only a topological vector bundle on U. Yeah, by no means one cannot hope to get a differentiable bundle. No, it's not possible. One gets only a topological bundle. Okay, now I also fix Dolbeau operators. They are also called, they are generalizations of D bar. Yeah, sometimes they are called semi-connections. I call them Dolbeau operators because I think that Dolbeau deserves to be quoted for this. So with coefficient Ck minus 1, satisfying what I call the formal integrability conditions. This means that the square, in a certain sense, I don't have time to define, is 0. What does this mean? So this means that we have induced holomorphic structures in the usual sense on the restrictions of the open parts. Yeah. So the holomorphic sections with respect to these holomorphic structures are precisely the solutions of the equation delta S equals 0. Yeah. So this is the relations between the Dolbeau operator and the holomorphic structure. Okay. So now a bit more technical objects in complex geometry. I look, so S is a real hypersurface, of course, has odd real dimension, cannot be a complex manifold. But what I can do, I can intersect the tangent bundle of S regarded as a subbundle of the restriction of the tangent bundle of U to S. Yeah, I can intersect with the image via the almost complex structure of we have on U. U is a complex manifold, so we have an almost complex structure. So we get a canonical almost complex distribution of S of codimension 1. Yeah, and I define the bundles lambda 0q S in the following way. I get in the usual way. So here, as soon as I get the complexified cotangent distribution of S, this splits natural in subbundles associated to in pairs of indexes PQ. I choose 0Q. Now, what is important for us is the Dolbeau operator we have fixed on A plus minus induced tangential Cauchy-Riemann operators between bundles on S. Here we have ES And here we have ES tensorized with the bundle lambda 01S I mentioned before. So in fact, I only need these bundles for Q is 1. Yeah. This is well known for the standard Dolbeau operators. The general case has been considered by Donaldson, yeah, in a paper which I discovered recently, and suddenly I noticed that it's a source, it's a very rich source of mathematical ideas.
Andrei, I am sorry, the time is over.
I'm very sorry. I thought it's up to 15. Yeah, I'm very sorry.
Okay.
I apologize.
1 minute, please. Okay.
Yeah, I think I will need less. So the gluing theorem says roughly that under these circumstances, one obtains a unique holomorphic reduction of our topological bundle I gamma, and that any locally defined holomorphic section with respect to this structure is a classic kappa up to the boundary. I will finish here mentioning that for the last part, yeah, of course, this is a text I prepared for a 50 minutes talk. There is the same gluing theorem can be used to prove a comparison theorem between moduli spaces. On one side, has a moduli space of framed holomorphic bundles along a hypersurface, yeah, which I introduced myself in collaboration with a collaborator, Matej Toma. And the other one is a fiber product of Donaldson moduli spaces defined by Donaldson. So I will stop here. I apologize for the delay. Thank you very much for your attention.